Hey Math 30-1, welcome to lesson 2 of exponents and logs. And in this one we're going to solve exponential equations. What is an exponential equation? Well, you've worked with them before in probably different ways, and we've always had to kind of use trial and error. Now we get to start learning some special strategies. An exponential equation is quite simply when the exponent has the variable, or the exponent is where you need to see the variable. And if simply you have an equation that has the same base as you see here, then we use a property that says if your bases are the same, then whatever you have in the exponent must be equal as well, right? And the only time this doesn't work is for C not equal to -1, 0, or 1. If any of those are the bases, then that property does not hold. If you can express both sides of the equation as powers of the same base, you can set the exponents equal to 0. So for example, how could 2 to the x be equal to 2 to the 4? Well, that would only happen if x was equal to 4. What if 5 to the 2x was equal to 6? What would x be equal to? Well, therefore, 2x would equal 6, and as a result, x would equal 3. That's the property we'll use to solve exponential equations. So here are the steps. So the steps for solving equations is, first off, to determine if the numbers that you see in the bases can be written as the same base. If so, we can go to step 2. If not, you're going to have to use a different set of rules. So this is solving exponential equations, and I really want you to underline, with the same base method. Same base method. You're going to find out later on that not everything is going to work this way. And I'll show you an example in a second. So if this works, you can go forward. If the question was something like this, when does 2 to the x equal to 7 to the 1? The property we just learned on the previous slide can't be used because, oh my gosh, you have different bases. Obviously, we can't equate these two exponents because 2 and 7 are not the same. So you have to have the same base in order to use this set of instructions. Right? So in lesson 2, we're going to deal with problems that we can use the same base method. So we rewrite the problem in the same base. We use the properties of exponents that you learned in lesson 1 to solve it. Step 4, once the bases are the same, we write the equation involving the exponents by setting them equal to each other, and we finish it by isolating the variable. Yay, us. Okay, so for example, we look at this and we say, whoa, they're not the same bases. However, knowing the laws of exponents, we know that 16 can be written with the same base as we might in 128. Both of them can be written as a power of 2, and so we do. 16 equals 2 to the 4, and 128 equals 2 to the 7. So if we rewrite them using a base of 2, we now have an expression or an equation that has the same base. We use the same base method, we use our exponent laws, and we get 2 to the 12x minus 20, 2 to the 14x minus 28. Therefore, 12x minus 20 equals 14x minus 28, so x equals 4. Right? Same base method. Well done. So now, again, if we have the same base, their exponents are equal. What about this? You try this one on your own. Spread your wings and fly. Come back and check the answer once you're done. Use the steps you did on the previous question. Now that you're back, the same base was 3. I rewrite it. I use my exponent laws. Therefore, 4x minus 6 equals 3x plus 12. X equals 18. And spread your wings on B, and then come back and see the solution. Now that you're back, you would have discovered that, wait a second, I can use any base for that one, because any base to an exponent of 0 is 1, so therefore 2x plus 4 equals 0, or x is equal to minus 2. And here's an example like we talked about. We are stuck in the mud because the only way we could do this is to use our graphing calculator. We could get, we can get x equals 2.09 by using something that we're going to learn. We could use logs, which we don't know yet. Now, if our life depended on it, we would graph y equals 3 to the x minus 10, and my solutions are the x-intercepts of the graph. So I would graph y1 equal to 3 to the x minus 10. My solutions would be the x-intercepts of the graph, because if you take it all to widen side, you would have 3 to the x minus 10 equals 0. So what does the x-intercept turn out to be? Check it with your calculator, but it should be somewhere around 2.0959. Okay? And on your test, I would say algebraically. Now, you could go back and do all of these questions with your graphing calculator, but you wouldn't get marks. So solve this algebraically. Again, same base. So spread your wings and fly. Come back and look. We have a base of 5 that we can rewrite these. And on the right side, that's really 5 to the minus 3. So now that we have exactly the same base, we can now equate their exponents. We've simplified, we equate their exponents, and we end up with an answer of x equals minus 1. You could verify it with your calculator by subbing it in right here or by graphing it, so you can always check to see if you're right. Once again, I want you to spread your wings and fly, and this is where you start to watch your exponent laws, because that's subtraction. Spread your wings, fly, use the same basis, see what you come up with. Now that you're back, I'm assuming you found out that the same base was 3, and you're going to pause here, or you did pause, and you realized, wait a second, I can't use exponent laws. If I do, you're stepping in a bucket of wrong, because if you try to use exponent laws, there are no exponent laws for addition and subtraction, even though they have the same base. So the only thing we can do is set them on either side, and we end up with the exponents being equal, and our answers are 3 and minus 1. We can verify our answers by checking out, does 3 work? Yes, it does. Does negative 1 work? Yes, it does. This is not the assignment. You'll be working on your assignment from your formative sheet that's in your workbook. I will see you guys on Monday.